Hey guys, how y'all doing? How's your day going? And if you're just starting, how was your night? Hope you had or are having an amazing and a beautiful day today. For those of you who don't know, you are currently watching your ultimate Python series. This is Python for the AI era. This course is going to be your solution to whatever programming problems you're having in Python, obviously. Unlike other programming tutorials that just start you off with a print statement and throw you into the field of full on coding, we're going to demystify the Python infrastructure, break it down simply simply as possible. Think of it as taking a tour of the engine room of Python, whether you're building APIs, you're training machine learning models, or you're doing local automation or simple automations. Understanding the ground which you're standing on is what is going to differentiate you from a regular Python developer and an actual Pythonista. Every single thing you need to know to make you stand out, to make your skills quantifiable and valuable in this era when AI is taking over is going to be covered in this series. You can also feel free to go and download the book, check out the GitHub. We have so much project, we have so much resources to make this the ultimate Python programming tutorial. So if you're interested in this, make sure to tune in, subscribe to the channel so you would know when we post a new video, follow us on all social media, and visit our website. After this tutorial is finished, we do have an exam which you can take to ensure you've understood the course, and it's more of like a certificate of completion. So sit back, grab your system, and let's get coding. Okay, so for this first episode, we're going to have a very simple roadmap, which is just going to cover some of the basic topics you need to have understanding of in order to actually work with Python. Now, I could easily start off by teaching you how to print in Python, but as we go on, you would obviously pick it up when I'm mentioning it, I've explained to you. But I think anyone can just go and Google how to print in Python. It's not really going to be worth a whole video now, is it? So our roadmap, the first is going to be covering the mindset. Then we're going to go over to the engine, then the garage, then the wiring, and then the blueprint. Just think of this as the full body of Python. Now, what is the mindset of Python? If you've attempted to learn Python before, or looked into it, or just been around someone who is in Python, you may have heard of something called the Zen of Python. I know, a very magical name. But the creator of Python, that is Gildo Van Rossum, I probably didn't pronounce his name correctly, realized very early that code is read way more than it is written. This was the guiding principle that encapsulated the Zen of Python. The Zen of Python is part of something known as the PEP. I'll touch on that a little bit further down in this video. But the Zen of Python is PP20. There are a bunch of other ones, like I said, I'll touch on the list down this video, and as the series goes on, I will introduce you to other PP. Now, this isn't a rule per se, it's more of a guiding principle which is supposed to help your, or it's like a design philosophy. You just helps to guide you to help distinguish anyone who writes code or a random person who writes Python code from a Pythonista, and your goal is to become a Pythonista. So in order to do this, we're going to just go over to our terminal right now, which is the point where I'll tell you to pick up your computer. But I feel I'll be doing you a misjustice if I just say open your terminal. I know it will be, will I say, degrading of me to assume you don't know what a terminal is. But if this is your first time attempting coding, then you probably don't know what a terminal is, or at least the Python interface in the terminal. So I'm going to treat you like a little baby, and we're going to just jump right in, shall we? Now, when working with terminals in Python, there are three main ones. There are a bunch of others, but there are three main ones you'd usually want to have at the back of your mind. The first one is the REPL, that is the REPL. This is the one that almost every Python developer uses generally. There is a more styled version called IPython, And lastly, there's one called Jupyter. If you are a data scientist, if you work with analysis models, you may already be familiar with Jupyter. So I'm just going to give you a quick brush on them. These are the main three interfaces we're going to be using aside when we start running our .py files directly. But these are the three main interfaces we'll be using for now that we're just starting, especially in this whole video. So the REPL, known as the read, evaluate, and print loop, is kind of like a debugging environment or an exploration environment. It's your interactive laboratory. While standard Python like provides a basic shell, which if you install Python, you usually come across that. If modern developers use IPython for more enhanced productivity, and you use Jupyter for more heavy duty exploration because it allows you to break everything into cells. So if you want to work with your basic shell, that is your REPL, you just open up your computer, go to your terminal, and just type Python. Before this update, you want to have installed Python. I think um I tell the new method for installing Python has changed. You don't just go install it, run it, and add it to your environment variables anymore. You now install a package where I don't know if it is just for Windows 11, but it's Windows 11 I use. But just go to the official python.org website, download Python, or if you are using a Windows, just go to your terminal, type Python, and it will redirect you to your Windows, what they call the Windows Microsoft Store, and you install it from there, and Python just automatically installed into your system, and then you can just run Python. This will open up a shell. You see three greater than signs, and you just know you're currently in the Python shell. Then inside there you can run Python codes, run your imports, build your functions. We'll see that shortly. But IPython is more professional. IPython is known, the full meaning of IPython is interactive Python. It's adds syntax highlighting, tab completion, and more major commands. So it gives you like which you put them within this percentage signs and run specific commands, which allows you to do things you cannot do in your normal Python shell. So for that, you would have to import it first to be able to work with it, and then you just run IPython to launch it. And lastly, for your Jupyter or Jupyter Notebook, as it's most people usually say it, you just install your Jupyter first using pip install, and then you can just launch it, and it takes you to a whole interface. It's visual, it's a web-based interface, but it works offline. So you can open up your folders, open up your files in there, write your the format for a Jupyter notebook is .ipynb. And Jupyter is not the only notebook you use. There are so many other ones, like Google has its own called Collab, but that is online. So if maybe you want kind of like the way you use your docs, your Google Docs, if you want to work with things that will be moving with you, so you can be working on one system and just pick it up on the next, you may want to look into using things like Collab. Once you start working on bigger projects, or when you start working with a team, you may find yourself using that more. But for now that you're just working yourself but just learning using it locally, Jupyter Notebook would work perfectly for you. But since we are just starting, we're going to just use the basic Python environment. So I'm going to be switching to my system now. Whilst I do that, which is going to be like a second for you, but you can pause the video, head over to python.org, and download Python, and just follow it's a very easy process. Just follow the instructions you see on screen, and we're going to go over to our terminal, shall we? Alright, so we are currently in my Visual Studio Code, but if you wish to just use your default terminal, if you're on Mac, you can just open up your terminal. If you're on Windows, you can just type in same there and it's going to open up your command prompt. But I prefer working in Visual Studio, so I'll just have one environment where I'm doing everything. So you can just open a random um folder in your system. This will be the folder where all the codes I'm going to be doing once I start working with files are going to be. So I just want to be in that environment. At the top here, we're just going to toggle panel or use the command Control J, which is going to open up our terminal here. So by default, Python, Windows opens up PowerShell. But if you don't wish to use PowerShell, you can just click here to view all the other different terminals that you have in your system. You can even install more extensions to give you more terminals, or install them directly into your Windows, and Visual Studio Code is going to pick them up. But we are going to use command prompt, which is the one I prefer. So whilst we're in our command prompt, we want to activate the Python shell, which is the REPL we spoke about earlier. But to just confirm you have Python installed in your system, you just want to do Python version. If you press it, you want to see something like this: Python, whatever version you're using should show. If you get an error, maybe that like Python is not a recognized command, just in your command here, type Python and it's going to redirect you to the Microsoft Store where you can install Python, or from python.org you want to install Python from there. But to activate the shell, you're just going to type Python and press enter. Now, once you do this, we're going to see a bunch of things. We want to see a change in where we are, so that would know like we've actually shifted. So we have obviously the version we're running, we have the date it was released, the time it was released. This is just going to tell you what device you're currently running on, so, or at least what OS. So if you see MSC, it's most likely they're running on a Windows, and there are like a bunch of other ones that will break it down. But yeah, let's just jump right into it. So the first thing we are trying to do is to actually see import the want to see the Zen of Python. So the Zen of Python, like I said, don't think of it as a constitution per se. Think of it more as, how I define this. Think of it as a design principle. So to do this, you just want to type import this, and we're going to see a bunch of rules. So these are the Zen of Pythons by Tim Peters. So you have beautiful is better than ugly, explicit is better than implicit, simple is better than complex, complex is better than complicated, flat is better than nested, sparse is better than dense, readability counts, special cases aren't special enough to break the rules, although practicality beats purity. Error should never pass silently unless explicitly silenced. In the face of ambiguity, refuse the temptation to guess. There should be one, and preferably only one, obvious way to do it. Although that way may not be obvious at first unless you are done. Now is better than never, although never is often better than right now. If the implementation is hard to explain, it's a bad idea. If the implementation is easy to explain, it may be a good idea. Namespace are one honking great idea. Let's do more of those. And we are going to touch on namespace in this video. But congratulations, I guess you can say you ran your very first Python code and it wasn't a print statement. Congrats. So we're going to just jump into the next one, which is the engine of Python. This is where we're now going to come across CPython and the GIL, your global interpreter lock. But yeah, let's just go for it, shall we? When you run a .py file, you may think Python is reading and executing it line by line. But even though Python is actually called an interpreted language, it actually follows a compilation pipeline. So the question now is, what actually happens? Your .py file is passed as the source code input to the lexer. The lexer is kind of like going to read it and start labeling the phases of what's going on. So what the lexer does mainly, it's converting your characters to something we know as tokens. So when you write a code, Python sees it as a long stream of characters. Then the lexer's job is to scan this stream from left to right and then group characters into tokens. A token is just a labeled atom of a code. So it consists of a type and a value. So let's say, for example, if we have x is equals to 10 plus 2, the lexer will now take this. Okay, we have the very first character x. We'll figure out what token type this is. It's a name and it's going to save x as the value. The next character we have is the equal sign, which the token type for that is an OP, or an operator. So we're going to have an operator with the value of the equal to sign. The next one we have is 10. So its token type is a number with the value of 10, and so on and so forth. So The addition sign is an operator with the value of, well, the addition sign, and 2 is a number with the value of 2. Then how does it handle keywords? It is programmed to recognize reserved words. An example would be if, which we're going to cover in a later video. So what we'll do is create a specific token type which is known as keywords. So this is going to be a keyword token for the if character. This now tells like the same that okay, we're in the next stage of Python to pay attention, and a large branch is about to start, or a large branch is starting. Then we have the significant white spaces. So when it sees the space at the start of a line change, it creates something known as invisible tokens. So there are three main invisible tokens we have in Python. The very first one is indent, which is generated when the number of spaces at the start of a line increases. So like this when it's heard things like indentation, which Python is a very heavy indented like language. We don't use braces like almost any other languages. You most of the way, like if you write a for statement and you put your column, the way we're going to know that this is within or this is under the for statement is by indenting it, and the way we know where we've left it is by I guess the denting, which is actually the next example of white space we have dedent, which is generated when the number of spaces decreases, and everyone's favorite new line, which is generated at the end of every line to show the completion of a statement. So once Alexa is done, the code becomes a token stream, which is just a clean categorized list of components that the parser can then use to build the logic tree of the program. So what happens in the parser? Well, the parser takes the tokens that are organized. It takes the tokens and then organizes them into something known as the AST, or the abstract syntax tree. This tree represents the logical structure of your code. So if you have a syntax error, the process is going to fail at this point because a valid tree cannot be built. So the parser's job is to just understand the grammar of your code, I guess. So how do you build a logic tree for yourself? We are going to visualize it in our terminal. But let's say we are giving a statement where we have result is equals to 10 plus 2 exponent 5, that is just multiplied by 5. The Lexa just sees it as a list of parts. So prior to this, we've already broken it down. We've gotten the operators, we've gotten keywords, if any, we've gotten the numbers and so forth. Then the parser knows the rules of Python language. It knows multiplication happens before addition. So it builds a tree where the multiply happens lower down. So its result can be fed up to the addition sign. I'll have a visual example of the tree on the screen so you can see that. But we have a sign which is our equals to, then we're going to have a name which is the result, and we're going to have a bin up which is the addition. That addition is a tree that is built, or is a branch that is built from the number which we have 10, and a bin up which we have multiplication. But that bin up too is also built from num2 and num5. So you're just building up your tree starting from the base and going up. So instead of a family tree where at the top you usually have whoever the first I mean the starting fathers of those family are, we are going to start at the base and now build upwards. But sorry, if you were to look at it like as an actual data structure, which is what Python is actually going to generate, you're going to have something that looks almost like, I don't know if I can say JSON or JavaScript. I don't really use those languages, but we'll have a model inside that. We're going to have our body, then we're going to have assign, then we're going to have the target, which in this case is the name result, and then we're going to have the value, which is going to be gotten from the bin up of at the left, your constant, which is the value 10, and your operation, which is add. So we're just visualizing, or this code we have here is what is just going to be visualized into that tree. So that tree is more for human understanding. It's not exactly how your computer is going to see it. And We have the structural mapping, so which is just like in each node in the tree, something it represents a construct. So we have your root node, your branch nodes, and your leaf nodes. So your root nodes are just the entire script. Your branch node is it like your keyword statement, if statements, for loops, functions, definitions, and then you have your leaf nodes, which are the actual values like 10, your strings, if you have any like hello or the names of of a variable like x. Then the syntax error, which is the gatekeeper in parse, is just the ultimate judge of your code's validity. So it's going to say, looking at it, it's going to start building your AST and it's going to be like, okay, I do not understand what this is, which is now what will now send an error to your terminal. So when you write your Python script and you attempt to run it, whatever error you see, the error comes from when you are in the parser, not the lexer. So think of it like, I'm trying to think of a good example that you understand. Let's say you speak English and I would speak Chinese, for example. You hired your initial translator. Let's say you took the person to like maybe a like a surgery lab or something, and the translator was just supposed to be bridging the gap between both of us as we're conversing. If the translator is someone who is not trained in the medical field, you can think of that person as your lexer. The person doesn't know if what you're saying makes sense. The person doesn't know if what I'm saying makes sense. The person just knows to translate what I'm saying. But if you have to get a translator that is educated in the medical field, this person will know if what I'm saying makes sense. They'll know if the word I'm using, maybe if you just translate it verbatim, it may not make as much sense in another language. So they'll know to better phrase it. So your parser is just going to take it and generate it better, and then it's going to output an AST. This AST is now going to be passed into the compiler, which is now going to translate it to bytecode. I feel anybody who has been in tech for a reasonable amount of time should know what bytecode is. Bytecode in Python is usually stored in a .pyc file, which you like always find in your PyCache directory. If you are working on basic Python folders, you may not see it, but once you start working with frameworks like Django, if you want to just check it now, go to your migration folder in any app you've created and you see a PyCache file there. You see all these .pyc codes. That's your bytecode. So bytecode is just a set of extremely simple instructions designed for a virtual process. So in this case, the bytecode is handled through the Python virtual machine. It's platform independent. That means if you take one bytecode, it will run on Windows, it will run on Linux, it will run on Mac OS, probably run on Android. And the compiler would then take this AST and will just turn it into instruction and action. So we were still working with our initial code. What was the initial code example I gave? Result is equals to 10 plus 2 times 5. So you just give it instructions. So this is when you're actually building an algorithm. Load your constant 10. What is just to push 10 onto the stack. So we have 10, which we're working with now. When I say load another constant 2, is just pushing 2 onto the stack. Also, we'll say load another constant 5 is pushing 5 onto the stack. So now we have all the numbers we're working with. We now want to run a binary multiplication. So we're going to now pop 2 and 5 so that it will take 2 and 5, multiply them together, and then push that value into the stack. So we're now going to have two values of 10 inside our list if you may. Then we now want to run an addition, which is just going to take the two tens we have, add them together, and then push that value. So why we need to pop, if you know what pop just means remove. We want to remove them from this because if we're just adding and pushing, we'll still have all the variables we've been working with. We want to remove the values, carry out the action on them, and then push the answer we have onto the stack or queue of what we have in them. Want now store the name as a result. So want to remove that 20 and save it to the variable. So this .pyc file, why does it need to be created, is to just help speed up execution process. So the next time you go and open up your project and you run the script, Python will first check if it has a .pyc file. You will now check if that .pyc file has, or if your main code has any change that has not been reflected in the .pyc file. And if no change has been reflected, it will just skip the whole process of the lexer, the parser, the compiler, and it's just going to load up your .pyc file directly into the virtual machine. So the CPython virtual machine, because most Python version that you run on your computer, like about 90% of the world runs CPython version of Python. There are so many other versions of Python, but the C Python virtual machine or your Python virtual machine is essentially a giant while through loop. It looks at the bytecode instruction, executes it, and moves to the next one. So it's just like while there are still more lines in your code, keep running and be executing the command. So the PVM doesn't just do math, it manages everything the program needs to survive, from memory management, garbage collection, and bridging between it and C programming. So let's just see a visual representation of what is actually happening in your code. This new version of Python isn't as, it's more simplified than the older versions we had, but we'll still get the idea. So I'll just open up my terminal so we can execute a code and get a grasp of what is actually happening. Okay, so we are just going to be kind of like experimenting with the Python internals. So in order to do this, there are a couple of models we want to import. So we want to first import the sys model. This is your main model we are actually need. This is probably the only one you truly need. This sys allows us to interact directly with our system. We're also going to install this and GC, but the sys is the main one we are going to be working with. So the first thing we may want to run and see is our Python version. Okay, so we're just going to run a print statement. What this print statement does is just display an output to the terminal so that people can actually see what you've been working with. We're going to use that sys we imported earlier, and in sys we have a function called version. So this will just let us know what version of Python we're running, which, if you remember when we triggered Python at first, we saw something like this. So the first thing we have obviously here is the version we're running. So we have the minor, which we have the major, which is the main version it's on. We have the minor, kind of like if you're downloading an app, you have 1.0, 1.1, and then we have the micro, which in this case here is a 2. So it just lets you know the exact version you're running. Over here we still have a version, then behind it we have a hex version of the Python which we have on this particular system. Then we obviously have the date, the time, and then we have the multi-arc, which just lets us know the device we're on. So Mac OS will have something like Darwin, or Windows you can have something like AMD Win32. My case is an AMD 64. You can have a Win32. Linux, I think Linux has a bunch really, because there are different Linux versions. So you can have like an ARM Linux, you can have a 32-bit system Linux. It's just to just let you have an idea of what your current system you're running on um is. Then another one we may want to see the output of is a more detailed version info. So I'm going to still do sys dot version underscore info. So this release level here just lets you know the exact. So when they are releasing a Python version, they usually have multiple versions that comes out, so they can have an alpha version, which means like early testing, so it's unstable. They have a beta version which is more stable but still undergoing testing. They'll have a candidate, which is the almost final, and the one which almost all of you have is the final version, which is the production ready um, version of your system. And let's also see sys implementation just for the sake of. So we'll have print sys dot implementation. So this one is way more elaborated. So the very first one here we have name. So the name we have is just going to tell us what type of Python we are running. Remember earlier I mentioned that there are different types of Python. So here we have CPython, which almost everyone in the world uses. It's built on C, is the most standard. We also have the PYP version, which is JIT compliant. We have the Jython version that runs on Java. We have Ion Python that runs on .NET and so on and so forth. So usually it just depends on what's that one is more of when you're working with like larger organizations, like you start going into proper model training. But for your day-to-day developer, you are running CPython. Then you have your cache tag, which just is more of like versioning and version control. Then you have your actual version info. So this is why I say so 3 is the major, 14 is minor, 2 is micro, or release level is final. Then you have your hex version, and then supports isolated interpreter is set to true. So the hex version is just a version encoded as a single integer. It doesn't really, at least not to you, doesn't really have much of importance. And yeah, let's just move forward to our actual bytecode disassembly. So we're going to build a function, which is what we're going to use, and we're going to try and like have a go and see what Python is actually doing, how the whole interpreted process works. We're not going to see verbatim what the Lexa is actually doing to our code. But remember when I spoke about like the load and everything, that is more of what we're going to be seeing a grasp of. Okay, so we want to just build a simple function. You don't really need to worry about the code I'm writing. Once we go into functions, I'm going to explain it more in detail. But if you're already a a proper developer and you're familiar with it and you're just here to understand the basics, you already know what I'm doing. I'm just building a simple function using the def keyword. We're going to, you can see here we had our indents, and we're going to just type return, which is just going to return the value of whatever is generated from the function we're running. And we're just going to do a plus b. So we built our function. So now I want to do this dot this, and we're going to say what we want to see more info, want to see being disassembled, which in this case is going to be the function which we created earlier, which is our add function, and we're just going to run that. So you can see this one is more, it's that code of the table I gave, but this is a more optimized way, which is an update that came with Python 3.14 of how it's breaking down the code we're working with. So at the very first line we have our resume, so it's a no up instruction, so it's not really giving much of like an action command for the system. Is used by the interpreter for internal bookkeeping, handling tracing, debugging events and generators. It just is the entry point for the function. Then in other version of Python, usually like the example I gave earlier on our table, you'd have all of these broken down into separate command, like load fast for A, load fast for B, then run your binary up. But you kind of like just grouped them together. So now we have load fast, borrow. So this is just a massive operation code, but it's similar to what we had on our table where it said load fast for A. So load the variable A into your variable which you're working with. Load fast again for B. So it's going to load your variable B, and usually you had like load fast 0A, so that is your very first, because in programming you start counting from zero, I think, except from like SQL and probably some other languages. Then you do your load fast one, then you now do your B, which is the second variable which you are pushing in before you now carry out your binary of zero, which is the very first binary operation, which is an addition. So you just want to perform an addition. But here we just have is loading both variable at once, then it's performing your addition on it, and then we now are using a return value to get the final output to just return the results we got from it. So the question you may now be asking yourself is, why do I need to learn this? Why do I really need to understand it? I could just learn to work with Python with my functions. Who really cares about how this works? It's as of now, when you're working with smaller projects, you may not see the value of it, but once you start going into more advanced projects, especially in a time when AI can write codes, which we basically written nothing, but in a time when AI can write codes, you want to give yourself an advantage over the AI. In order to get an advantage, you actually have to understand the ground you're standing on. You have to understand, like, because truly understanding this is just how is going to be your differentiation, which is kind of like the main motto for this whole series. Anybody can learn how to code. Most people don't need to learn how to code. You just need to have $20 to pay for an AI. But once you understand in this case, your virtual machine, how it interprets your code, you can now give you a better understanding of your GIL, which is your global interpreter lock, which one of the main time this comes in hand is when you start going into reference counting, like how Python manages your memory. So let's just quickly touch on GIL. If you are enjoying the video so far and want to get access to more of our detailed resources and learn more on this topic and many other topics, I would advise you check out the book which was created for this specific series. It's called Python for the AI Era. The links to download the book will be in the description below. Don't forget to download, rate it, and share it with your friends. I promise there is so much more to learn in the book, most of which we'll cover here, but still so many things that the book will cover at length. Feel free to use both resources to learn. You can never learn too much now, can you? Okay, so because Python manages memory using reference counting, if you had simultaneous threads modifying the exact same object in a memory at the exact same time, you tend to get a catastrophic memory corruption. So the GUI acts as a traffic hub. It ensures only one thread executes a bytecode at a time, simplifying memory management. So the question is why? Mainly for memory safety. Python uses reference counting for memory manage, so the GUI will save it by like locking execution. If you had, let's say, a bank, and your bank, this usually known as like concurrency. So if you had a bank account, and let's say you had $3,000 in your bank account, you had a debit card on that account, you could use your mobile app to transfer from that account, and let's say you gave your card to someone to go out and purchase something. You have 3,000 in the account, and for some reason the person is trying to withdraw 3K out of your account. You are also at the same time, at the exact same time, trying to transfer 3,000 to another person. So if it allowed both of those actions to take place, so allowing both threads to run at the exact same time, $6,000 will leave your account, but you do not have $6,000 in your account. So what I would do is like kind of like say, okay, let this one run first, and then the other one run. Usually, you want to like set like rules that will guide you. This is when you want to now make your system run parallel to each other. You have rules that shows which one you're prioritizing and whatnot. But the internal flow for this is a thread acquires the GUI, it executes the Python bytecode, releases it periodically every few milliseconds or after every operation, and then another thread will now get a chance to now act once the GUI is open, or once there's a spot for a thread to come in. So this also controls how we work with content switching. That is how Python is going to be switching between the different threads. So it could be maybe after a number of bytecode instructions, or it could be during a blocking IO operation. Maybe you're downloading something. So within that period when you are waiting for it to be downloaded, another thread can take place for it to work. So this now brings a very common question that some people may have: is Python inherently bad at concurrency? So even though it may seem like that to some people, Gil is not a bug. It's a highly deliberated design choice with very specific trade-offs, and you can easily navigate them once you understand how to do that. The absolute crucial point here is to know the difference between IO bound operations and CPU bound work. So threading works beautifully for tasks like web servers or fetching API data, because the GUI is automatically released when the Python is just sitting around waiting for maybe network or a file IO tag. So multiple threads can happily wait for data concurrently. But if you are doing something that is more heavy or CPU bound, like number crunching or like training the model, threading will just create a heavy bottleneck in your system. So in cases like this, you would have to use something called as the multiprocessing library to spawn completely separate processes which bypass the shared GUI to give you the feeling of parallelism. So we can visualize this. I'm just going to pull up a small program that we can just use to test and get a visual rep of how this actually works. Alright, so I explained your GUI is released during error operations. So when a thread does like network IO, maybe downloading, requesting, or you're doing it in your files, the GUI is released allowing other threads to run. So we're going to kind of like see this. For this, let's just use a normal PY file, and let's just okay, sorry. I just realized as I was editing the video that my mic turned off. So a large part of everything I said when I was explaining how the girl um works was cut off. So I'm just going to run you through it as quickly as possible. Ignore any code you're seeing now. This is the same power address that projects are. If it's not what I'm explaining, then it's as of now of zero content. You want to read that part of the video. But the first file I touched on was the guild.demo file. So here we're just explaining how IO bound operations work with GIL and why threading works for it. And I gave a popular example of that was if you are making requests or if you're downloading or making well API request, I guess. So for this example, we imported the threading, the time, and the request model. The time is just so we can see how long it takes to for each task to be completed. So at the very first here, I defined a fetch model, which is going to take a URL, is then going to run a get request on the URL and print the status code, whether it's 200, 44, or whatever. Oh, shit. Then we're going to define the URL. So I also explained that if you use times four in on a string, it's not going to work like if you're doing normal numbers when you do two times four. Instead, it's going to create that string like multiple times. So in this case, four times. We're now going to get the start time of when we want to run the operation. We're now going to use threads, which is now going to run a loop on each of these URL, taking the URL, passing it into our fetch function, and then whilst it's fetching, start running the next one instead of waiting for it to finish or waiting for a response to be gotten before we run the next tag. Then I now did another version. We're just doing it with normal loops where you would do for you in your rows. Take the first one, do it, wait for it to finish. Take the second one, do it, wait for it to finish, and so forth. Now we're just going to compare the time it takes for each of them to complete. I think that was the first Python file. So that was probably the video where I told you how to run a Python file. Running a Python file, you put Python and the file name. In this case, our file name is gil underscore demo dot py, and we're just going to run it. Give it a minute. Oh, I'm in the virtual environment. So even visually, you can see how long it's taking for this first one to how long it took this first one to do, and you're seeing how long now it's taking for the second one to be completed. So if we are using threading for the IO bound operation, it's going to take 2.72 seconds to run all four URLs, and it's going to take about 14 seconds to run them individually. My network obviously played a part on how slow it took, but now let's do CPU bound. For CPU bound though, we have to use threading. We're going to have to use this multi-processing model, because here we're doing larger operations, and no operation really has a moment where it's taking a break from your guild. So what we'll do is instead use like pools, creating different like as if we're going to be creating different guilds basically. So this is the function we obviously want to run, and this is the number we're running into the function. Then when we want to now do, so in this case I'm doing 9 pulls, so I'm just doing first guild, second, third, up to ninth. You can do as many as your heart desires, really the world is your oyster. And then we're going to get the end time when that takes for everything to finish processing. I also did another one where if we're passing all the numbers into the functions individually, and we're going to see how long it takes for that one to be completed. This one's file is CPU underscore bond dot py. So it's quite a large number. But yeah, we'll just see how long it takes for that to be completed. So the very first process we using multiprocessing has been completed in 18 seconds, and we can see the second one is still going. So I'm giving it like about 30 seconds or so. I feel 30 seconds is faster than the computer is saying it is. Okay, 47, 48 seconds. So this is just to show you like these are actually things you can also apply to projects you work on. When you're doing something that demands you working on multiple things at the exact same time, or working on a large amount of data, maybe like processing, I'm trying to think of real life. It's mostly everything that's comes behind is models, but there are so many other times when you could use it. So it's just things you can just adapt into your skills to just help speed up the time. Like I say, if you're working with smaller projects, this time difference don't mean much to you, but when you're working on time sensitive projects, that's when you're not going to start seeing the value of actually taking all of this into account. So yeah, I'm just going to continue to just the videos. I just wanted to add this because my mic got cut off and I didn't want to do a voiceover. Okay. Before we continue, let's take a minute to thank our sponsors for this video. Our sponsors are the reason why we are able to bring this detailed series to you for free. Our first sponsor is Vultrin. We spend so much of our time securing our code, our databases, and our digital infrastructure, but we rarely think about the actual physical infrastructures keeping us safe when we step away from our decks and move through the real world. That is exactly why Vultrin was built. Vultrin isn't just a simple safety app, it's an uncompromising zero knowledge personal protection ecosystem engineered for zero failure performance. When you trigger an alert, Vultrin's network routes your emergency data with minimal dispatch latency. So if you're commuting late, or traveling through unfamiliar areas, proactive features like safe walk and the automated deadline switch actively monitor your progress. If a crisis occurs, the system automatically activates a localized evidence vault, capturing and locking ambient logs behind encrypted databases so that your data remains tamper-proof and completely your own. Do not leave your personal safety your personal physical security to chance. Build a reliable safety architecture for your everyday life. Go to vaultry.com right now and secure your world. That is vaultryn.com and secure your world because your safety is non negotiable. I would also like to thank our second sponsor, Techinovoom. In the modern technology landscape, the gap between having a visionary product concept and deploying a robust, high performance platform is massive. Most companies fail not due to lack of ideas, but due to a failure in architectural execution. That is what Technovum tries to solve. They are an elite technology and engineering firm dedicated to transforming complex challenges into highly scalable, enterprise ready digital ecosystems. From deep technical system architecture and production ready machine learning pipelines to building complex consumer facing mobile platforms, Technovum designs softwares for the AI era. They don't just build application, they engineer the underlying structural infrastructure that allows your software to operate at maximum efficiency, scale seamlessly under load, and withstand rigorous security standards. Their engineering framework is optimized for performance, speed, and uncompromising reliability. Stop letting technical bottlenecks slow down your market delivery. Partner with a technical powerhouse that builds for the future. Visit technovum.com.ng today and let them engineer your next breakthrough. That is techinovom.com.ng. Now back to the video. Okay, so we need to now step back and look at where your code actually lives because avoiding conflicting packages, mismatched Python versions is very severe to like maintain reproducibility of your project. For example, you're working with a team and you're pushing your code, so you need other people in your team to be able to install it and have it actually run proper on their end. You have multiple projects you're handling on one system, you don't want their versions to be clashing. And like for MacBooks have a default Python that is already in the system. You don't want your project to go and mess with that, so you don't have to like format your system or whatever. So to do this, there are three layers we need to focus on. The first one is your version, which we use PyEnv. It just handles your Python versions that are running your system. Next, we have our virtual environments, which is the VNV. It isolates project packages in your system. So just think of it like every single project you're starting has a whole new computer sort of that you're working with instead of working with the same computer where your previous project was on. So you have to reinstall whatever packages you're going to be using. You can install the specific version of that project that that particular project the specific version of that package that the particular project needs to avoid clashes and whatnot. Then you have your packages, which is the PEP, where all it just handles installing dependencies in your system. So whenever you're working with PEP, you want to make sure you're never using PEP on your global system. You must always be running it in a virtual environment. But the question is now, how do you actually start working with this? So we're just going to switch over to my computer once again. Alright, so if you want to use PyEnv, we would have to install it. So obviously the commands are a bit different on Mac. You'll be using a call. So I'll leave all the commands you need in description below. Hopefully I remember. But since we're on Windows, this is the command. So it's best we do this in our PowerShell. I'm just going to paste that. Make sure you're connected to the internet, obviously. I'm just going to let that run. Okay, so after you've run that, you want to restart your Visual Studio Code. Once again, to ensure everything, like ensure your terminal is refreshed. So a way we can just confirm if it's been installed is to just run pynv slash version, and we should see what version of the pynv we have. Now, how do you actually manage Python versions once your pynv is installed? The first one is installing specific versions. So you do pynv and you run the install command, then you put the exact version of Python you want to install. So you can do Python 12, and it's going to install that exact specific version for us. Alright, so after this we can install another version. Let's do maybe 11.9. Now I'm going to show you under command. I'm not going to run it by myself, but if I want to change the default Python version that my global system uses, I'll just say pyenv global, and then I'll just state the exact version I want. Same way, if I want to do it for just this current directory or inside, I'll just do pyenv local, and that will be my default Python version. So let's do for local, since it's just this directory we're in. Which ones are the ones we installed? Let's do 3.12.3. So let me just confirm. So you can see my Python version here has changed, but if I leave this directory, you can see now that is now saying, because we've not set a default one. But let's go back. What's more this directory code? Okay, so if you want to say a list of all the Python versions you have, you can just do pyenv and versions. So it will show you a list of all the ones you have, and it's saying sets by showing the, yeah. And yeah, next one, want to go into virtual environments. So there are multiple ways to handle virtual environments. What some people may do is to do Python dash m, then venv, then whatever name they want the virtual environment to be. I just use virtual environment to do my own, so you just do pip install. Yes, I know I say don't install pip to your, like, without a virtual environment, but pip install virtual env. Then if I want to create a virtual env, I'll just do virtual env. And I, whenever I'm creating a virtual env, I usually like starting the name with uh period. So just do .venv. So you can see at this place here a file was created. And now to start it, so if you're on Mac, you just do source, then the name of your virtual env .venv, using this particular slash, because that is slash used for it directly, is bin slash activate. I don't know if Linux is the same. I do not have a Linux computer, so I cannot really help. I'll probably just go with that in the description if I remember. And for Windows, you just do the name of your file .venv slash script with a capital letter S, script slash activate, and we should see the name of our venv here. If you want to close it, you just post deactivate. You want to activate the game. So if you come to this folder that was created, we want to look for the file which we run. So this is the script file which we ran, and inside there we have our activate command. So that's just what we're doing. We're just opening up the file. So now that we are inside your virtual environment, if you are activating in PowerShell, it's different for PowerShell. So if you just do .venv slash scripts slash activate. Oh shit, why the fuck do you work? It's not supposed to work. Okay, this is the first one because it usually doesn't. Let me see if it will work in a different PowerShell environment, because it's like actually doesn't work. You usually have to do dot PSL with the, like, this is the file you usually use for, like, it's this one. This is the PowerShell file. This is usually the one you have to activate. I'm sure there's a reason behind it. I honestly don't know why, but this, like, first time in my life is working. So open PowerShell. Let's see. I should have to go to the directory. So this CD downloads. New folder. This is a very ugly folder name, by the way. Yeah, let's go of that space. Let me, I think from the file I can open a new folder inside it. I know it works for CMD, but it work for PowerShell? No. Let's rename the whole folder. Things we do because we are lazy. I'm just stressing myself. You know what? It's not worth it. It's really not worth it. I'm going to just continue our life. But hey, it works, I guess. But if yours doesn't work, maybe I just got lucky, deactivate. What you'd want to do is not slash the name of your file .env slash the scripts slash activate. Oh my god. No, it's not working. I guess that doesn't work for me anymore. I'm sure there's a reason why the normal one is working. I should probably look into that because this doesn't work. Could it be because of the PyEnv? To be honest, I honestly don't know. Sorry, I couldn't help you out with that one. But if you install the PyEnv, then that will probably work for your PowerShell. So now that we're inside here, we can now start pip installing. So when you're working with, so I just, oh gosh, no. So I'm going to install few models which we'll use in the future, but I want to show you something. So let's just do fast API. So when you're working with pip install, you just do pip install fast API. If you want to uninstall, you just do pip uninstall fast API. Fast API. If you want to specify the version, you can add like an equal sign, but we'll just do this and install it first and wait for that to finish running. Hopefully we can finish this before my system goes off. Oh wait, no, let me connect my system. I have an inverter. So I've connected my system to the inverter. It's connected. So once you install, if we were in Python, we'll be able to tell the models installing. But if you want to see it for yourself, you can just do pip freeze and it will list out all the models that are inside this virtual environment you're working with. Then usually when you start pushing to GitHub when you work with teams, we have something called the requirements.txt file. That is kind of like what lets your team know what versions and what models they need to install. So you usually just do pip freeze greater than and whatever name you want the file to be. You can be any names, but we have like a fixed name we usually use, which requirements the txt. We're just telling it fetch all the models we have in this environment and push it into a new file, which is going to be this .txt file here. And you can see all the models with the exact version. Then when we want to install, we just do pip install /r requirements.txt, and it's going to install all the models that we have inside the folder. Oh well, now you understand the environment. But these environments are somewhat of the older way for managing all the environments you have in your system. So we have modern tools which kind of like handles everything at broad in broad. So one of the most important one we usually use is UV. If you are part of people that have been experimenting with all these new AI models where you set them up locally like Olama, you'll see one of the Olama installs you use the UV to install it. So this is a ROS based environment manager that is it's like 100 times faster than the standard tools we use. So while you still have more modern-ish tools like poetry, which are incredible deterministic, they use dependency log and turn it into tables using pyproject.toml standard. But UV acts more like a high performing sports car. So it handles every single thing from management, your virtual environment to global packaging, caches, and everything is just built in together and it's faster. So let's let's try that, which when we're working with lighter projects, we are still going to continue using our normal virtual environment. But once we start going into more complex projects like fast API and so forth, we're going to now switch to using this. So before that, I want to have like a base understanding of how to work with .log files, how to work with .toml files, and everything. So let me just switch. To do this, obviously, we're going to have to start installing again. I'll leave a link to everything we need to install in the description below so you can check that out for yourself. Okay, so to install we're going to start with poetry. To install that, we're just going to put this code. You can either pause or just copy it in the description. Okay, it's been installed. So we just want to run poetry version. So if yours doesn't come up or it is an error, then you can just add it to your environment. But if you want to start a project in poetry, you just initialize it. So poetry init. So what should we name it? Tests. Because why not? We'll just say version 0.1.0. Don't have any description. I guess we're using fast API, right? What version of fast API? Zero shit 0.136.3. So these are toml file, which is just kind of like a guide, like a base documentation on what your project is, and this is just normal version of Python. If you push code to like certain servers, you may be familiar with this already. So if let's say we want to add a new model to what we're doing, let me just put this up. We want to add a new model which we want to use in our project. We'll just say poetry add, and we'll just put the name of what we want to add. So we can see request here. Then if we want to maybe install it too just for like local development and for like testing, We can now do poetry, add, then want to group, dev, and we can now put maybe let's use PyTest because that's one of the most popular stuff for testing. And now you can see dependency groups, dev. Wait, let's see if it's going to allow us to create new groups. Never tried. Ooh, it works. Okay. Well, yeah, once you're done with that and you want to just leave the poetry show, you just press exit and it closes it up completely. So we're back to our same way we had before. And if you want to run a file using poetry, you just do instead of just Python, you just do poetry run, then Python, then the name of the file you want to run. Which files do we have that do not take so much time to run? Let's do Gil underscore demo. That's PY. Then if another developer on your team now pulls your code from GitHub and wants to install everything you have set up, they'll just do poetry install. All right. Well, I guess there you have it. Next up, I want to now look into UV. Okay, so my mic also died whilst I was recording the section for UV, which I hadn't realized. So I lost over 20 minutes of audio, but I'm just going to re-record it. I already have it installed, but I'll still walk you through. The link to install UV will be in the description also for whatever device you're on. But just think of UV as the modern holy grail of Python. It was created by Astral. Unlike poetry, it covers all the three main layers you have in when you're working with environments or when you're managing your environment. So it handles every single thing from start to finish. So I would obviously have the link for you to install, and you just find the link in the description, install it. Once you install it, you can just run UV dash version to confirm that it has actually been installed into your system. So if you don't see anything, you may want to check if you've added this into your environment variables. So some of the cool things you can do on UV is firstly, Python version is similar to what PyEnv does. You can use UV to install different versions of Python. So you just do UV Python install. Then here you can have a list of all the versions you want. So you can do 3.12, you can do 3.13. So I already have this installed, but you can install as many versions of Python as you want. If you want to create a fresh project in similar to what we did for poetry, you just do UV init. So it's not going to work because we already have a project here. So I'm going to just delete this. This was all I used in the other video. So let me just delete that. Let me create a new folder. I'm just going to switch to that directory, and now we can initialize a new project here. So if we come into this folder, you see it's going to create a readme file for us. This is a markdown file where you just let people know what your project is about. If you work on GitHub regularly, you should be familiar with the readme file. We have a toml file similar to what we have for poetry. Let us know the name, the version, the description, and whatnot. Then you have a main file. This is a default Python file that is created first, and obviously a git ignore. These are just things you'd want GitHub to ignore when you are pushing it. Then if you want to create a virtual environment using UV, like I said, it handles every single thing. You just do UV VNV and it's going to create a virtual environment for us. then it's showing you what code to use and activate Sage virtual environment. So let's just activate it. But this is the same code .bmv slash script with a capital S slash activate. So now you can see NNN virtual environment is activated. Then if you want to add or handle dependencies within the project, let's say you want to install a particular model, well, you still use fast API since that's all we're using. So just do uv add fast API. So if we come to our terminal here, you see fast API has been added as one of our dependencies. Then if you want to add development only dependencies, you do uv add dev, then the name of the model you want to add, pytest. So that is also added to our form. If you want to run a file using uv, you just do uv run and the name of the file. So it's going to run it for us. If you want to force your local environment to match the log file, you just do uv sync. And yeah, I think that is everything we need to cover for uv. As we progress down, we're going to dive deeper into uv. If you've worked with more advanced tools, like I don't know if you're familiar with olama, if you've tried setting up llms locally, you if you go to the official Lama website, you usually see a place where they tell you to install using UV. UV is one of the fastest modern tools people use. I think it almost works 100x faster than even some of the other tools we use. So once we start going into more advanced projects, we're going to find ourselves using UV more regularly. Alright, next we're going to be switching to the wiring, which is the namespaces and your LEGB rules, like LGBTQ. Have you ever wondered how Python knows which variable you mean when you just type X? Let's say you have a program where you have multiple times when a variable X is called. How does Python know which one to actually access? Namespace is nothing more than a simple dictionary mapping names to objects created by every module and function. So when you write x is equals to 42, Python just goes to update a dictionary that tracks your variables, mapping x to the value of 42 by ensuring that every single module, function, and class is its own very or has its own very own dictionary. Python elegantly prevents massive name collision across your entire code base. When you call a variable, Python doesn't just guess where it is, it searches strictly downward in the exact order known as the LEGB rule. That is your local first, then enclosing function, then the global models level, then global models variables, and finally built-in functions like your len and your print. It just travels down that list, grabs the very first match, and then it stops looking for any other possible or better match. Alright, so we're just going to create a file for the namespace. So we're not really doing much, we just want to see how Python handles calling a file. So we're going to create a global variable x file. This is just a string with the name global. Then we're going to create an enclosing function. So just call it outer. And inside this, we're going to create another x string. And we'll just call the value for this one enclosing. And inside this, we're going to create another local namespace. So we'll just define an inner variable, and we'll have a string for this, which will just be local. So inside this local, we want to print x, and the print for this one should be local. That should be the value that is printed to the terminal. Once we obviously have to call the inner function of b, but once we leave this, we want to print the outer x also. Then we'll have to call the function too, and after this we want to print the global. So there isn't really a built-in function called x, so we don't really have a way to test the b, so we'll just print a built-in function, I guess. But yeah, let's run it. Now I'm the manager, so I'm running I'm running a Django. Oh my god. What's the other one again? Name space underscore demo dot py. So it's printing out the local, then the enclosing, then global. Okay. Now this resize search order also applies to models via a list called sys.path. So if let's say you want to load a file, Python will usually take to account the current directory you're in before looking anywhere else. An example, the random model, which is a pre-existing model in Python. But if you were to name a file inside your working directory random.py and you attempted to import random, instead of importing the random model, it's going to import your own file which you created. And if you try to now access a function inside the random model, it's going to raise an error. This is because, well, your file doesn't have it. That is why whenever you're naming files, you always want to try and use as unique enough name as possible. I don't know if you get what I'm trying to say. But next we have the blueprint, which is type annotation. So this is your best tool for preventing bugs before your code even runs. It's important to know that Python still remains dynamically typed at runtime. Adding an annotation saying a variable is an integer won't stop Python from assigning a string to it while the code is actively running. Like you saw when we're creating variables, we didn't have to say, oh, this variable is an int, like when we were like you would do in other languages. However, tools like MyPy, Pyrite, and Pylance catch bugs before code runs. They essentially act as executable documentation. It will ensure future you or your entire team know what data shape is expected. If we look beyond basic type, there are valued advanced concepts here. So we have some concepts, some tools, and what you use them for. For example, we have the generics, which is type var, which is safe for multiple type handling. We have metadata, which is annotated. You mostly come across this when you're working with fast API. So these are like runtime validation schemas, and we have doc type, which is protocol. So it's like structural subtyping. So you find yourself using this more for documentation, error handling, but you can easily also use type conversion to ensure that like the input you are receiving, especially when you are using the input function or the input using function, you convert it to the actual data type you want, and then you can use error handling in case maybe you're expecting to get a number and the user passes in a string and you try to convert that, that's going to raise an error, but you can then catch that error and now print out a custom error to the user to avoid your code from crashing. One thing, whenever you're building software, you always want to ensure that whether an error arises or not, your code ends or your program ends smoothly. You should always be the one ending your program, whether it's that it came to an end or you handled an error properly. We're going to jump into error handling a couple chapters down. But yeah, so before I wrap this video up, I want to touch on PEPS a little bit. So it's a very brief section. Like I say, as we go further, when we come across certain PEPS, you'll be aware of it. We've already touched on the Zen of Python, but PEPS just stands for Python Enhancement Proposal. So it's just a guide that teaches you what Python does and why certain design decisions were made, the trade-offs that are considered, and the alternatives that were rejected. So I have a brief list of the available PEPs we have. So PEP 8 is your style guide, is the baseline formatting standard every Python developer follows. We have PEP 20, which is the Zen of Python, which is your philosophical foundation. We have 257, which is doctrine conversion. It's just how to write doc strings. Doc strings are just ways you usually document your functions. We have 343, which is the weak statement. We came across that earlier when we're attempting to look at IO bound and CPU bound functions. So these are just context managers, foundations of safe resource management like files, logs, and DB connections. We have 380, which is yield from is matter wipe of delegating generators, the foundations of async and wait internals. We have 484 typing, the entire type annotation system, everything we covered previously. Then we have async and await, which is the native coroutine syntax. We have 526, which is variable annotations. There is like when you have x and you have your column int is equals to 5. It's just required for data classes to just like I said earlier, let you know the data type you're expecting. We have data classes, which is a decorator. It eliminates boilerplate like the int, the REPL, and the EQ. We have 572, which is the words operator. That is a colon and an equals to sign. It's just an assignment expression, so it just allows you to chunk assign stuff. So we're going to cover that very soon. We have generic types, that is 585, like the list int instead of like the capital list int when you're working with the list. It's cleaner, fewer imports are needed. We have 604, which is the union with I don't know what to call this symbol. That symbol that is like a street. So we have 634, which is match and case. It's just structural pattern matching. And we have 703, which is a no guild mode, which is experimental free trading Python. It just helps to change Python concurrency fundamentally. But yeah, that's all for this video. There was just a basic intro to Python, just understanding how it works. And I feel before we go, we should just have like a little project we work on. I'll put the project on screen, but it's just Python environment auditor. So it's build a CLI tool that inspects your current Python environment and produces a health report. That is the Python version, installed packages, virtual AMV detection, and a compatibility check against requirements. So the requirements are it should detect and print sys.version, sys.executable, platform.system, platform.release, and whether the user is inside a virtual environment. It should read the requirements.txt for each package, use imports.util.findspec to check whether it's installed, and import lib.metadata.version to get its version, flag missing or outdated. Then print a formatted table, the package name, required version, installed version, status if it's okay or missing. Use only the standard library, no third party formatted library. Then add a fixed flag if pass, run pip install requirements or txt for any missing packages using subprocess.run, print what was installed. Save the full report to environment underscore reports.txt with a timestamp header. Print a summary line, X packages okay, Y missing, Z outdated. So I'll put up a sample of how the output should look. It's everything we covered. I've created a Git issue where you can push your code to your own GitHub in a public repository and put the link in the issue so that we can just have like a little community around it and everyone can see what everyone is saying. But yeah, without saying too much, thank you all for watching. Don't forget to like, subscribe, share this video if it was helpful. In the next video, we're going to go into more advanced Python basics where we're going to cover things like your variables, data types, bitwise operators, and so forth. So I'll see you guys in the next video. Don't forget to check out all my other socials, and the link to the full complete textbook, which is guiding this whole series, will be in the description below, so you can go grab that for yourself. My GitHub will be in the description. My TikTok is mobile.dex. My Instagram is underscore dot underscore PRAIZ. And if you have any questions, feel free to leave them in the description below. But yeah, I'll see you guys in the next video. Have a beautiful rest of your day. Bye, guys.